Hello everybody, welcome to part 5 of the linear and nonlinear relationships topic. Last lesson we started our work on parabolas and we looked at special forms of the parabola. We had y equals x squared as our standard parabola and we moved it around and flipped it upside down and whatnot. And today we're going to be looking at a more general version of the parabola y equals ax squared plus bx plus c. When we have our equation in this form, there are a few things that we want to be able to do. We want to be able to sketch it, and in order to sketch it, we want to find features such as the x and y intercepts, the axis of symmetry, and the vertex. So let's use the parabola y equals x squared plus x minus 12. We'll use this parabola to help us do some of those things. Now first we should be able to notice what a, b and c are. A is 1. Just matching it up. B, the coefficient of x, that's also 1 in this particular parabola. And what is c? Well, c is the constant term at the end. That's the negative 12. We've got to make sure we include the negative there. Alright, let's start off by finding the y-intercept. If you recall from our work on straight lines, if we want to find the y-intercept, we need to set x equal to 0. Remember, anywhere along the y-axis, the x-coordinate will always be 0. So, in our equation, y equals x squared plus x minus 12, let's make x equal to 0. So we get 0 squared plus 0, take away 12. Quite easy to see that this parabola must cut the y-axis at y equals minus 12. Or we could put it into a coordinate form and say that the y-intercept is the point 0, negative 12. Okay, but what about the x-intercept? Well, likewise, if we want to find the x-intercept of any graph, we can set y equal to 0. Anywhere along the x-axis, the y-coordinate will always be 0. This one's a little bit trickier though, because when we make y equal to 0 in our equation, we've still got a bit of work to do. Remember, parabolas are quadratics, and from our work on the quadratics topic, we saw how we could factorize quadratics and solve for the x value when a quadratic is set equal to 0. So, if you do need any help or a refresher on how to solve quadratics, maybe check out the quadratics revision video that I posted a while ago. With this quadratic in particular, we can factorize it by looking for factors of negative 12. So what are some factors of negative 12? Specifically that add to give us this plus 1 over here. That's right, negative 3 and positive 4. Negative 3 times 4 is negative 12, so they are factors, and negative 3 plus 4 is positive 1. So they're the factors that we want. There were other factors of negative 12, like negative 1 and 12, or 1 and negative 12, 2, negative 2 and 6, or 2 and negative 6, or even 3 and negative 4. But none of those, when we add them together, gave us plus 1. Alright. Once we have our factors, negative 3 and 4, what we can do is put them into brackets. We can say that 0 is now equal to x take away 3 times x plus 4. Once again, if you have doubts about how we can do that, just think about doing the opposite of expanding factorizing, sorry, which is expanding. If we FOILed this expression and did the first, the outer, the inner, and the last, we would see that we would get 4 terms: x squared, 4x, minus 3x, and negative 12. And when we simplify, we would get x squared plus x minus 12. Okay. The reason we factorize is because now that we have 2 distinct parts, we have the x minus 3 and we have the x plus 4. Either of these can be set to 0, because if one of them is 0, then it doesn't matter what the other thing is, because 0 times anything is 0. So we can either have x minus 3 equal to 0, or we can have x plus 4 equal to 0. These are just 2 simple linear equations to solve now. For x minus 3 equals 0, x must be equal to 3, and for x plus 4 equals 0, x must be equal to negative 4. So we have our 2 x-intercepts. The x-intercepts for this parabola are x equals 3 and negative 4. Or, as coordinates, 3, 0 and negative 4, 0. 3, 0 and negative 4, 0. Okay. Let's go on to, before we go on, if we deal with a quadratic that's difficult to factorize, we can always use the good old quadratic formula. Remember that one? X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Whew, bit of a mouthful. We can use that though, especially if we have a quadratic that is difficult to factorize. Okay, let's move on now to the axis of symmetry. Remember, the axis of symmetry is the line about which our parabola is symmetrical. Now, one thing we should note, first of all, is that the axis of symmetry lies halfway between the 2 x-intercepts. The axis of symmetry lies halfway between the 2 x-intercepts. That means, if we wanted, we could just take the average of those 2 x-intercepts. So in this case, 3 and negative 4, what happens if we take the average? However, if we don't want to do that, we can use an equation. We can use an equation for the axis of symmetry, which is this. X equals negative b over 2a. So we could just use that. In this case, we know that a equals 1, b equals 1, and c equals negative 12 for this specific parabola. So let's substitute our values in. X equals negative 1 over 2 lots of 1. And that just simplifies to negative a half. Now hopefully when I asked you before what is the average of 3 and negative 4, you might have been able to work out that it's negative a half. If we have negative 4 here and 3 here, right, that's a gap of 7. So we want to go 3.5 units in from either side in order to get to our middle point. our middle point there will be at negative 1/2. Okay, 3.5 units in from either side. From this side or from this side. But using the equation x equals minus b on 2a, that's a pretty good way to find the axis of symmetry as well. Okay, finally, the vertex. Remember, the vertex is the turning point of our parabola. And the turning point, that lies on the axis of symmetry. So that means that it has an x coordinate of minus b on 2a. Or, for this particular parabola, an x coordinate of negative 1/2. So what we can do is substitute in x equals negative 1/2 into our original equation to find the complete coordinate. Y equals x squared plus x minus 12. But we're going to replace x with negative 1/2. So there we've rewritten y equals x squared plus x minus 12 by substituting in negative 1/2 for x. A negative times a negative is a positive, and 1/2 squared is a quarter, minus 1/2 minus 12. That gives us a value of negative 12.5. So the vertex has coordinates negative 1/2, negative 12.5. Alright, with these bits of information, we can graph our parabola. Before we do that, the fact that we have x squared, so a positive x squared, means that our parabola will be concave up. Concave up. We talked about concavity. We wrote some notes briefly on concavity last lesson. Concave up. Okay, think about the u in up. That means that our parabola is going to look like a u, as opposed to concave down, which goes the other way. Alright, we have our y-intercepts, we have our x-intercepts, we have our axis of symmetry, and we have our vertex. So let's go and graph this parabola now. Our y-intercept we worked out was negative 12. So let's plot that first. We'll do that in green. So going down to negative 12, 3, 4, 5, 6, 9, 10, 11, 12. There's our y-intercept. Our x-intercepts were 3 and negative 4. 3 and negative 4. Here's negative 4 on our x-axis, and here's positive 3. So there are our two x-intercepts. Now our axis of symmetry was given by the equation x equals negative 1/2. So this is a vertical line at x equals negative 1/2. Here's negative 1/2, and so let's draw, just dotted, our axis of symmetry vertically down the page. So it is about this line that the parabola will mirror. It will be exactly the same on either side. Finally, our vertex. Our vertex was at the point negative 1/2, negative 12.5. So it lies on the axis of symmetry, and it's just past, just a bit further down from the y-intercept. hopefully we can see if it's going to be turning down here at this vertex and going up through the two red dots at the x-intercepts, we can see that it is concave up. It is a happy parabola, we might say. So last step is just to connect our dots. We want to make sure that it's a smooth parabolic form as best as possible. So coming down through the first x-intercept, doing a bottom turn at the vertex, through -12, and back up. Just missed it. Back up through the other x-intercept. And there is our parabola. Okay, just labeling the points to make it clear. It's always a good idea. And there we have it, how to graph parabolas when they're in the form y = ax² + bx + c. Until next time.